Everyone, welcome back you all in this new video. Here we are going to see the professional approach for the manual design of cantilever retaining wall with flat backfill. This complete problem we are going to solve in a few important steps. In the first and second step, we are going to see the problem statement, initial sizing of the retaining wall and calculation of the forces and moments. In the third and fourth step, we are going to see the calculation for the earth pressure, stability checks against the sliding, overturning and pressure. In the fifth step, we are going to see the design of the toe slab, hill slab and vertical stem. In the sixth step, we are going to see the scheduling and detailing as per the design results. At the end of this video, I will let you know some bonus tips and tools so that you can do this complete lengthy design in just of 3 to 5 minutes only. So for better understanding of everything, it's request with you all, please watch this video till the end. Now, first of all, try to understand the problem statement. A cantilever retaining wall is required to retain a earth mass of 3.7 meter height above the ground level. So there is a cantilever retaining wall which has to retain a earth mass of 3.7 meter high which is above the ground level. The backfilled soil has a unit weight of 19 kN per meter cube and the angle of internal friction has given 30 degree. The exposure condition is moderate. Assume that the SBC of the soil which the retaining wall has to retain is having 120 kilonewton per meter square and that the coefficient of friction between the soil and the concrete is given as 0.6. We actually have to design a reinforced concrete retaining wall by considering the grade of concrete as M25 and grade of steel as Fe500. So here we have given a retaining wall, cantilever retaining wall with a flat backfill. There is no inclination of the backfill that your retaining wall has to retain. So what does mean by retaining wall with flat backfill and the retaining wall with inclined backfill? Let's try to understand. So in our proposed case, we have given the case first. We have to design the retaining wall which has to retain a backfill which is the flat one. There is no inclination in this backfill. But when you are going to see this example, in this example, your backfill is having the inclination. So the calculation something different for this kind of retaining wall which is having the backfill as inclination and the retaining wall which is having the backfill as flat. So there will be some difference between the calculation of these two different types of the retaining wall. One retaining wall is subjected to flat backfill, one retaining wall is subjected to inclined backfill. But in our proposed example, we have given the backfill as a flat, there is no inclination. In upcoming video, in the next example, we will see the design of the cantilever retaining wall going to be subjected to the backfill as with a inclination. So as of now, we are having the problem with a flat backfill. So in respect of this problem statement, I am going to write all the given data here. So height of the earth to retain as 3.7 meter above the ground level, that is given in your problem statement, 3.7 meter above the ground level. The unit weight of the soil is needed to take as 19 kilonewton per meter cube as per your problem statement, 19 kilonewton per meter cube. Angle of internal friction has given 30 degree. Safe bearing capacity of the soil as 120 kilonewton per meter square. Coefficient of friction between the soil and concrete is needed to take as 0.6 only. Material for the concrete as M25. Material for the steel or rebar is needed to take Fe500. So this is the complete data is given for the purpose of deciding the reinforced concrete retaining wall. So in the light of all this given data, we are going to start the solution. So in the first step, we are going to find out the depth of the base and we are going to set out initial sizes of the retaining wall in the first step. Let's try to understand what actually we are going to do in step first. So basically, we have to find out the sizes. What should be the depth of the base? What should be the width of the toe? What should be the width of the heel? What should be the size of the stem? This is called as stem. This is called as toe. this is called as hill. The portion under the backfill area we are going to call it as hill. The portion outside or other side of this hill we are going to call it as toe, and this is called as stem of your cantilever retaining wall. We need to find out the sizes of these. So for this calculation, firstly we are going to calculate, this is the ground level, okay, the earth on this front side, this is the side of your backfill, this is the other side. So on this other side there is what ground. From this ground, at what depth your base of the slab of the retaining wall will be, that we need to calculate. So basically in the first step we are going to find out the depth of the base, up to what level the depth of the base of your cantilever retaining wall is needed to take, that we have to calculate. So the formula here, it is given that SBC of the soil divided by unit weight of the soil inside bracket 1 minus sine of the theta plus 1 plus sine of theta of square. If you are going to put all the values here, we are getting the value as 0.7. So theta means angle of internal friction we already have given as 30 degree, so that we are going to put here as 30 degree. So finally we are getting the value as 0.7. But to be on safer side, we are going to take the depth as 1 meter. Depth of your base from the ground on this other side, on this other side of your backfill. This is the side. So from here we are going to consider as what, 1000 mm. Actually demand is what, 700 mm. So we are going to take it as 1000. So here depth of the base has been calculated as a 1 meter. Now overall depth of the retaining wall, that is going to become, so actually what, the height of the earth to be retained by your cantilever retaining wall is given as 3.7 above to this is what, from here it is given as what, 3.7 up to the top. It is given, if you are going to measure it from here to here, it is 3.7. Now this 1 meter we have calculated. So finally total height of the retaining wall is going to become, including of this depth, it is going to become what, 1 plus 3.7. Finally overall depth of the retaining wall or height of the retaining wall is going to become 4.7 meter. Now we have to calculate the width of the footing or width of the base. We have to calculate first. So in the literatures or in the recommendation, it is given that we should have to consider the full width of the base or footing of the retaining wall to be considered as 0.5 times total height of the retaining wall to 0.7 total height of the retaining wall. This we need to consider. So therefore I am going to put the values here, 0.5 multiplied by 4.7 to 0.7 multiplied by 4.7. So the range is coming as 2.35 meter to 3.29 meter. So actually you are free to choose any width of footing between this range. You can take 2.35, you can take 3.25, or any of the value in between of this. So here we are going to consider total width of the base of your retaining wall as 3.3 meter. So actually we are rounding of this as 3.3 meter. This is the final value. Now width of the hill. Width of the hill means the size of the base to be considered under the backfill. Okay, if you are going to see this figure, so you can understand that this is the backfill, flat backfill. So under this backfill, whatever the size or width of the base you are going to consider, it is going to be called as what, hill. And on the other side it is going to called as what, toe, and it is going to be called as what, hill. So we, how much width of this hill to be considered, so this is also what you have to take with the approximation. Here it is given, width of the hill will equal to 0.5 times total width of the base. So 0.5 times 3.3, it is going to become 1.65 meter. But here also, to be on some safer side, because we are going to take more size, so we will be on safer side. That's why we are going to adopt 1.7 meter finally as round off value. Thereafter, what thickness of the base slab means base of your retaining wall, what thickness to be adopted. So total height divided by 12. So 4.7 meter. So it is in mm going to become 4700 divided by 12. It is coming out to be 391.7. Again, we are going to adopt it 400 in mm. So adopt the stem thickness at the base as 400. Yeah, one important thing, let's try to understand here. Actually, what we are doing, whatever the depth of the base is coming or thickness of the base slab is coming, or you are adopting as here 400 mm, so the same thickness we are going to consider as the width of or thickness of the stem at its base. Thickness of the stem will be different at its base and at its top. Try to understand, the thickness of the stem will be different at its base and at its top. So as of now, we are going to consider the thickness of your stem at its base as equal to the thickness of your base slab. So base slab thickness we have adopted as 400 mm. So that's why we are going to adopt stem thickness at its base as 400 in mm. Hope that you all understood. So minimum 0.3 meter as per the recommendation. Recommendation what is saying that the thickness of your stem at its base should be taken as what? 0.3 meter as per the recommendation, means 300 mm. Minimum what? It should be 300 mm. We have adopted as what? 400 mm. That's we are safe. At the base it is what? Finalized 400. What about what on the top? So on the top it is recommended that minimum 0.2 meter as per the recommendation. It should be 0.2 meter means what? 200 in mm. The thickness should be at the top, should be present. So what I am going to consider here, we are going to consider as 225 mm. The thickness on the top we are going to consider. Finally, as we are knowing overall height or depth of your cantilever retaining wall as 4.7 meter. Now I want to calculate stem height. This stem height I want to calculate. So it's very simple. 4.7 minus 400 mm. Okay, 4.7 means 4700 mm minus 400 mm. If you are going to do this, so you will get actual height of your stem, this height. So when you are going to design the stem, at that time we need to have this height of the stem. So we are actually having height of the stem will equal to 4700 minus 400. Finally we are having 4300 mm is actually the height of your stem. So what all the dimensions of your cantilever retaining wall here we have decided. Okay, so base, its so width overall we have adopted as 3.3 meter, hill 1.7 meter, depth we have calculated as 400 mm, stem at its base we have considered it as 400 mm, on the top 225 mm. That's all done. Now you should ask a question, how we can calculate the toe width. So it's very simple. We are having total width as 3.3 meter, this minus 1.7 meter, this as equal to this 400 minus 0.4. So if you are going to do this calculation, you will automatically getting the width of your toe. So total 3.3, okay, minus, again I am repeating, 1.7 meter minus it is 0.4. Okay, so you will get 1200 mm as a toe width. So this calculation we have completed here for the dimension of the cantilever retaining wall. Now in the next step we are going to do the calculation of all the forces along with the earth pressure. So firstly try to understand what does mean by the earth pressure. So as you can find from this figure, actually your earth mass is present on this side as well as your earth mass is present on this side. So the pressure which is going to be exerted on your retaining wall from this side of the soil mass is called as active side or active pressure, or you can say active force, and the pressure it is which is going to be exerted from this side is called as what? Passive pressure, passive force. So these pressure coefficients from this active side, the pressure coefficient we are going to represent by Ka, and the pressure coefficient from this side we are going to represent by Kp. Unless you are not calculating this active pressure coefficient and passive pressure coefficient, till that you are not able to calculate the actual force coming on your retaining wall from the soil mass from this side, and force coming from this side of the soil to your retaining wall. These two forces we have to calculate, and this is possible to calculate by calculating the pressure coefficient as Ka and Kp. So these two calculations firstly we are going to do in our step. So earth pressure coefficient Ka, active earth pressure coefficient, 1 minus sine of 30 divided by 1 plus sine of 30. After doing this calculation we are getting 0.4, 4 times 3. Passive pressure coefficient Kp, same formula is there, only the sign difference here on the top positive and in denominator it is negative. We are getting the value as 3. So both the pressure coefficients we are having. Now at this time the important point you have to note it here, as of now we are giving the importance to this side soil mass because it is a more important than that of this side. That's why we are going to do the calculation for this side as of now. So how much the force which is going to be imposed from this soil mass to this retaining wall we are going to calculate. And how you can calculate it, come to this force due to active earth pressure. So Pa will equal to, it will be very simple as 1 by 2 Ka gamma E into H square. Here in the figure you can find it out how you can calculate how much the force is going to be imposed from this soil mass to this retaining wall just by knowing the area of this triangle. So its base is what? Ka gamma into H multiplied by total height. Total height is what? 4700 mm. So this calculation, area of the triangle, you know very well how to calculate the area of triangle. 1 by 2 base into height. Your base is what? Ka gamma H, and height is your total height of the wall. So this formula I am going to put here to calculate the Pa force. Ka 1 by 2 Ka gamma into H square, where H is equal to 4.7 meter. If you are going to put all the values here, you are getting the force from the active side as 69.95 kilonewton. This calculation has been done over the 1 meter length of the wall. Try to understand all the later calculation we are going to do for the 1 meter length of the retaining wall. The entire calculation, if you are going to see here, the length of the retaining wall may be very long. That may be 1 kilometer or 100 meter, 200 meter, 500 meter, 1 kilometer, that we are not knowing. And even in your problem statement it is not given what is the length of the retaining wall is. So here I am going to consider the length of retaining wall is very much larger. That's why we are going to consider, or we are going to do the calculation for the 1 meter span of the retaining wall or 1 meter width of your retaining wall. So here the calculation of the force has been done over the 1 meter length of the wall. So total active force is 69.95 kilonewton. Now moreover to this lateral load calculation, we are going to do the calculation of the gravitational force that is going to imposed on the soil through your retaining wall. So this calculation we are going to do in our table. So this table 1 is calculating the forces and moments over 1 meter length of the retaining wall. So firstly we are going to calculate the weight of footing or the base of the retaining wall. So if you are going to see your base, so this is actually the base of your retaining wall. So we are going to calculate the base of this retaining wall as a weight, and this is going to be represented by W1. One thing we are calculating. Secondly, we have to calculate the centroid of this area, the base of this rectangular fitting, the centroid of this area we are going to calculate from the reference of the toe. From the toe we are going to find out the centroid of this base area. So this calculation we are going to do in this table. So this is what gravity load we are going to calculate, lateral force we will also calculate, and distance from the toe we are going to calculate, and thereafter by multiplying this load with the distance we will come to know the moment. So firstly we are going to do the calculation for the footing or the base of the retaining wall. So the formula is, firstly have a look, this is the total span of your base and thickness of the base is 400. So 3.3 meter multiplied by 0.4 meter as the height, and over the 1 meter we are going to do this calculation, so that is understood, not needed to write. So I need to know the base, I need to know the thickness, I need to know the length. So the calculation is going to be done over the 1 meter length. Thickness we are knowing as 400 mm, so it is going to become 0.4 meter, and the width is 3.3 meter. So these all values we are going to put here. Thickness as 0.4, width 3.3 meter, and now it is what density of the material. So your base is going to be made up of a reinforced cement concrete. So concrete is there majorly, so 25, you know very well the density of the concrete we are considering. So after multiplying all these values we are getting the value of gravitational force from the base of the retaining wall as 33 kilonewton. Thereafter this load is going to be concentrated from the center of this base. So this center is coming obviously at the half of your base of your retaining wall. So 3.3 divided by 2, you are getting the center point, so that we are going to write here as 3.3 divided by 2, 1.65. Now if we are going to multiply this 1.65 with 33, you are getting the value of 54.45 kilonewton meter. It is the moment. It is actually what? Moment. Thereafter we are going to calculate the second thing, that is stem triangle. So when you are going to see your stem here, so two sections we are going to create here. So one section is your triangle. If you are going to see this part, it is in triangle, and this rest part is what? Rectangle. So there we have to do the calculation separately for the triangle. Thereafter we are going to do the calculation separately for the rectangle. So here what? W2 I am going to represent it, and here this rectangle I am going to represent by what? W3. So W2, W3 we are going to calculate here. So when you go to your calculation, stem triangular, stem rectangular, both we are going to do. So firstly what? 0.4 is the total thickness of your stem at its base. Stem is having 0.4 meter at its base. Now you have to subtract this. So this is what? 0.225. 0.4 minus 0.225, you will get this value, the base of your triangle. So that we are going to do the calculation here. Have a look. 0.4 minus 0.225, and we are going to do the calculation for the area. So 1 by 2 base into height of the stem. So height of the stem is what? 0.4.3 meter, and 1 by 2 it is the base. 0.4 minus 0.225. Overall this area going to be multiplied with 25 kilonewton per meter cube as the density of the concrete. After doing this calculation we are coming to the value of 9.41 kilonewton. This we have to multiply with the centroid of that triangle. So centroid of that triangle, how you can calculate it? So the centroid of this triangle will come, suppose if you are going to do the calculation for the centroid of the triangle. So have a look here how you can do this calculation. Suppose this is my triangle. So this is the point from where we have to calculate the value. So suppose this is the centroid of this triangle. So this is what coming, if you are going to count from this point, so it is going to become 2 base by 3. This base is 2 times base of 3. This is what that centroid. So suppose you are coming to this. but it is the calculation from here up to this. You are coming to the point of the centroid. Suppose the point of the centroid is this one, so this distance you are knowing, but we are doing the calculation from this point, so we have to measure it from here. So this is 1.2 meter plus this distance that we will calculate. So this distance you have to add in that, then you will come to know total span from the toe to up to the centroid of this triangle of the stem. So same calculation here has been done. So have a look, triangle 1.2 plus 0.175, how this value is coming. So total 0.4 base of your stem minus 0.225, so you will have this span. You will have what? This span, okay, at the base. So this is what has been calculated, 0.175. Then you have to take it as what? 2 times divide by 3. So 1.2 plus 0.175 multiplied by 2 by 3. So we are getting the centroid point from the toe as 1.32 meter. Now 1.32 meter you have to multiply with 9.41. So you will come to know the moment as 12.38 kilonewton meter. So this is the triangle. Now for the same stem we have to do the calculation for the rectangle. So for the rectangle it is very simple. The size of the rectangle is what? Have a look here. The width or we can say the thickness is 225 mm and height is what? 4.3 meter, and the material will be your again concrete. So we are going to put here 225 multiplied by height 4.3 multiplied by 25. So total weight or the force in kilonewton 24.19. Now this again we have to multiply with this centroid. So again I am going to do the calculation for the centroid. So centroid of this 225 is obviously be half. Okay, 225, half of that we will get the value, and that we have to calculate from the toe. So from the toe it is 1.2, and this base we already have calculated 175 mm plus half of this 225. So you will get total value of the centroid of this rectangle from the toe. So that I'm going to do here. Come back to the calculation. 1.2, 0.4 minus 0.225. So you will come to know 0.175 plus 225 divide by 2. So finally the centroid point from the toe, it is going to become 1.49. Okay, now this 1.49 going to be multiplied with 24.19. So finally coming to the value of 35.98 kilonewton meter. This is the moment. Now the first thing, try to understand here. We have done the calculation for the base, thereafter for the stem in two part. One is the triangle, second is your rectangle. Now this soil will also imposing the load in gravitational direction. So this I am going to represent by W4. So W4, how you can calculate? It's very simple. The soil we are going to consider for the width of the hill. So total width of the hill what? 1.7 meter, and thereafter height of the soil we are going to consider. Have a look here. Height of the soil has considered 4.3 meter. Above the base we are going to consider, okay, and width is what? 1.7 meter, height is what? 4.3 meter, and density of the material, now it is not the concrete, it is what? Soil. And the soil density in our problem statement has given that 19 kilonewton per meter cube, the density of the soil. So I am going to multiply with that 19, 4.3 multiplied by 1.7. So load concentrated due to the soil 138.89 kilonewton. Now the centroid point we have to calculate. So the centroid point of this soil, how it will be, try to understand. This is the soil. In this figure you can understand it very well. This is the soil W4. So the centroid will be half of this span, 1.7 divided by 2. So half you will get. Then this 0.4 meter, then plus this 1.2 meter. So overall the calculation is going to be done here. 1.2, 0.4, 1.7 divided by 2. Okay. So finally we are getting the value of 2.45 meter from your toe. Now this value of the axial force going to be multiplied with this distance, we are getting the value of 340.28 kilonewton meter is the moment. Now why these moments we have calculated, try to understand. Here if you are going to fix this point of your toe, we are doing the calculation by fixing of this point. So this W1 force as creating the clockwise movement in respect of this fixed point. Then this stem weight W2 and W3 both are going to create the clockwise movement. Then this W4, we are having the distance in respect of the toe, it is again going to create the clockwise movement. Now there is what lateral force also that we already have calculated in our earlier steps. Here you can see we just have calculated the lateral force imposed from your soil over your retaining wall. So there we have done this calculation, this lateral force from the soil which is going to be imposed on your stem. So it is what going to create the anti-clockwise movement. These all weights which is going to be concentrated in downward direction in gravitational direction, it is going to create the clockwise movement, and this lateral force is going to create the anti-clockwise movement. So what to do with this clockwise and anti-clockwise, we will discuss it later. So as of now, it is also one kind of load we are going to consider in our table. Lateral load we have calculated as PA. So here we are going to write it is the lateral force. So one lateral force is what, as an active force component pH 69.95. This is the value, nothing but we have calculated in this equation 69.95 kilonewton. Here we are going to write, okay. Thereafter we are going to multiply this with the distance from the toe. How you can calculate distance from the toe? When you are going to see here distance from the toe, so toe from its base, and this is going to act at a distance of 1.75 meter. So it is the base, this is the toe. Suppose I am going to call it as what, toe point. This is the point. From this point we have to measure. So if you are going to calculate this distance, it is the triangle. So it will be what, whatever the height, total height divided by 2. If you are coming from the point side, so we have to consider 2h by 3. But if you are coming from this side, okay, where the 90 degree is there, if you are coming from this side, it is to be considered as what, h by 2. So this height we are going to consider. That's why total height divided by 2. It is the geometry, not needed to explain, but for your understanding I am discussing this point here. So it is going to become 1.75. So the point of action of the load from this fixed point of the toe, it is 1.57. So that we are going to put here 1.57. Sorry, not h by 2, it is h by 3. When you are going to see from this side, it is h by 3. And when you are coming from the top, when suppose we are coming from the top, from this side, if you are going to measure it, it is going to become 2h by 3, right? So this correction you have to do. So now h, total height 4.7 divided by 3, it is coming out to be 1.57. This 1.57 to be multiplied with a 69.95. So now we will get the moment. That moment here is not written because it is the what, creating the instability in your retaining wall, because it is creating the anti-clockwise movement. And when you are going to consider these all movements are actually clockwise movement, which is what adding the stability. This is what causing the instability. So they are both opposite to each other. So as of now here, this movement is causing the instability, this movement is causing the stability and adding the strength to your retaining wall. So in this way we have done this calculation. So finally here it is what calculated overturning movement. This movement is going to cause the overturning in your retaining wall. That's why 69.95 multiplied by 1.57 meter, so 109.82 kilonewton meter is causing the overturning, and this 443.09 causing the stability in your retaining wall. They both are opposite to each other. So hope that you all understood the concept of doing the calculation of the load and their respective centroidal distance from the fixed point, as in our case we are considering as toe. In some of the calculations you will find the distances is calculating from the heel. So we are considering in our calculation from the toe, not from the heel. Now after multiplying this load and the distance, we are getting the movements. So this overall calculation we have done in this table. Now after calculating of all the loads as in gravitational direction due to the self weight of the retaining wall and its components, and the load due to the soil on the back side of your retaining wall and their perpendicular distance from the toe, and finally by calculating of the moment. So all kind of stresses we have calculated in this table. After calculating of all these stresses, the next step is to do the design of your retaining wall and finding out the reinforcement, means what reinforcements are required to provide in your retaining wall that we need to do. But prior to that, we need to perform the stability check. Stability checks means we are going to ensure that whatever the sizes of your retaining wall, sectional sizes means the width of the base and depth of your base and height of the cantilever of your retaining wall, its base, its top. So whether these section sizes of this retaining wall is stable or not under the application of the load, that we have to ensure whether your provided retaining wall can sustain its stability or not, that we have to ensure, and that is nothing but called as stability checks. So the stability of your retaining wall we are going to perform in a three way. One is against the overturning, against the bearing pressure, and against the sliding. So we are going to check whether your retaining wall is safe against the overturning or not, against the bearing pressure or not, and against the sliding or not. So that we have to ensure, and this is recommended by your IS 456 2000 clause number 20 page number 33. So when you are going to see your code, it is recommending to ensure the stability of your retaining wall. So basically the first stability check we are going to perform as overturning. So as we have seen that our retaining wall is going to be subjected to the lateral load, and our retaining wall is also going to be subjected to the gravitational load. So two things will happen, that is what your lateral load causing the instability in your retaining wall. Due to this lateral load, your retaining wall will comes under the instability, and this all gravitational load is going to provide the stability to this retaining wall to maintain its positioning. Due to this lateral load that we already have calculated and this perpendicular distance, there will be the movement is going to be developed over the retaining wall. So it is going to be what rotated, as you can find here. If your lateral load and the moment caused due to this lateral load is going to become dominating, so what will happen, your retaining wall get tilted or get moved in this direction, and that we don't want. So to prevent the tilting of your retaining wall, we have to ensure the restoring movement. So the weight of the wall and the weight due to the soil in gravitational direction should be such that it should control in anti direction of your movement of the retaining wall due to this lateral load. So this check is nothing but the check against the overturning. So we already have calculated the overturning movement in our earlier calculation, overturning movement, and this is coming from the lateral load and its perpendicular distance from the base. So after multiplication of these two things, we got the moment as 109.82 kilonewton meter. So here it is written, and we have taken this value from the step 2. Thereafter restoring movement. Restoring movement, as I told you, means the weight of the element of your retaining wall, base and its cantilever portion. It is what adding the load, and that load it is in gravitational direction. So what will happen, it is resisting the movement that is going to be developed by this lateral load. So as we are considering in the instability stress in movement. That's why we have to consider the restoring force in case of movement. So that also we have calculated. The restoring moment is 443.09. so this is nothing but your restoring moment. Here restoring moment you can call it 2 or resisting moment you can call it 2. So it is 443.09 kilonewton meter. That is taken from the table number 1. Now we are going to reduce this resisting moment by 10%. That's why we are going to consider only the 90% of this resisting moment, because we are going to take some kind of safety as recommended by your IS 456. So IS 456 has said that in case where dead load provide the restoring moment, means self weight of the retaining wall and the soil in gravitational direction, only zero point 0.9 times the characteristic dead load shall be considered. So whatever the dead load due to the retaining wall weight is going to be considered, that is only the dead load I am going to call. So we are not allowed to consider 100%. We are going to reduce it by 10%, means we are going to consider only the 90% of the restoring weight or restoring moment we are going to consider. So here in the calculation we are going to reduce it by 10%, only 90% I am going to consider, and in denominator overturning moment will be considered here. So after doing this calculation we are getting the value as 3.63. that should be more than of 1.4 as recommended by your IS code. In the IS code it is written that the stability of the structure as a whole against the overturning shall be ensured, so that the restoring moment shall not be less than the sum of 1.2 times the maximum overturning moment due to the characteristic dead load, and 1.4 times the maximum overturning moment due to the characteristic imposed load. So overall we have to ensure our stability of the retaining wall in this pattern or in this way, that what here this ratio factor of safety against the overturning, that should be more than of 1.4. so I can say that my section sizes of the retaining wall is safe against the overturning. That's why hence it is safe against the overturning. Hope that you all understood the first check. Now the next check we have to perform, that bearing pressure check. In this check we are going to ensure that whether the base size of the retaining wall that you have adopted is safe or not, and whatever the stresses going to be developed at the base of the retaining wall from the soil below is within the limit or not, that we have to ensure. So in this bearing pressure check we are going to ensure that three things. What first thing, the base of the retaining wall is adequately decided or not. Secondly, we are going to check the upward soil pressure at the base of the retaining wall are within the limit or not of your given SBC of the soil. And third is that the settlements are within the limit or not. So if you will ensure the pressure within the limit, then we can ensure that the settlement will be within the limit. So this all checks comes under the check against the bearing pressure. Here firstly we are going to find out the location of your resultant force from the gravitational load of the self weight of the retaining wall and the lateral load going to be caused due to the soil behind the retaining wall. So this we have to find out total weight. So total weight we are knowing very well, as we have calculated total load in gravitational direction as 205.49. that is including the self weight of the retaining wall, means its a component, as well as the self weight of the soil on hill in gravitational direction. That all combination is coming out to be 205.49 kilonewton. This is the load. Thereafter we have to know the moment due to lateral load, that we already have calculated as 109.83, and restoring moment, that is 443.09. So basically to find out the resultant force, the load in gravitational direction, load in lateral direction, its a resultant force acting at what point from the distance of toe. At what distance your resultant reaction is going to be formed. So distance of the resultant reaction from the toe will equal to as x1 equal to movement as restoring moment minus overturning moment divided by overall weight. So after doing this calculation, we will come to know the distance from this toe is 1.62 meter. Now eccentricity we have to find out. Eccentricity, we actually going to find the center point of this base, and center point of this base will be obviously half of the width of this base. So total width of the base, whatever is there, half of that, it is b by 2, it is b by 2. Now from this center of the base and your resultant, this is nothing but your eccentricity. That is very simple. Eccentricity will equal to half minus your x1, the distance of resultant, the point of resultant force. So after doing this calculation, we will come to know that the value is 0.03 meter as the eccentricity. Now this value should be less than of the b by 6. So that is middle third of the base. So again b by 6 is nothing but 0.55 meter. So your eccentricity is less than of 0.55. That means it is safe. Hence the resultant reaction is within the middle third of the base. So that is the good thing for the stability of your retaining wall. Now here 6e divided by b, we are getting the value of 0.06. This value will be needed to calculate the upward soil pressure from the base of the soil, means whatever the soil present under the base of the retaining wall, that is going to exert the pressure. So what pressure is going to be developed, we have to calculate maximum pressure and minimum pressure, both we have to calculate. So maximum pressure should not be more than of your SBC of the soil, and the SBC of the soil we have given as 120 kilonewton per meter square, and minimum pressure should not be less than of 0, means this value should not be negative, this value should not be more than of 120. So your minimum and maximum value should be in between 0 to 120. It should not be less than of 0, it should not be more than of 120. So this calculation we are going to do. So here maximum pressure calculation is what? Total weight divided by width of the base inside bracket 1 plus 6 times eccentricity divided by b, that we already have calculated here. So after doing all this calculation, we will come to know the maximum pressure going to be exerted by the soil at the base of the retaining wall as 66 kilonewton per meter square. It is not mm, it is actually the per meter square. Now secondly, minimum pressure 205.49 divided by 3.3 minimum pressure inside bracket 1 minus 6 times E by B. So here 1 minus 0.06, so 59 kilonewton per meter square. By mistake here it is written as mm square, actually it is what? Kilonewton per meter square. So I will correct in final file. So it is what? Kilonewton per meter square. So maximum value is 66 and minimum value is 59. So it is minimum value is more than of 0, that is safe, and maximum value is less than of 120, that is also safe. So finally, hence we can say that there is no tension in the soil below the footing. This is what? Base, or base you can call it as footing also for this cantilever portion. So now factor of safety against the bearing will be what? SBC of the soil divided by your maximum pressure as 66, and this value going to be multiplied with 0.9 as a safety. Now after doing this calculation, the factor of safety against the bearing we are getting 1.64, that should be greater than of 1.4. If this value means the factor of safety here is coming out to be less than of 1.4, means what? At that time what to do? You have to resizing of the base of the retaining wall. You need to either increase or decrease. You have to take another trial. If you are not getting your factor of safety against the bearing more than of 1.4, so here I am finally going to say my retaining wall is safe against the bearing. Now the next check that we have to perform is the check against the sliding. So it's very interesting check to perform for the stability of your retaining wall. So when you are going to see your retaining wall, so retaining wall is going to be subjected to lateral load, as you can find from here. So this lateral load will become a cause of shifting of this retaining wall in this translational direction. When your weight or your retaining wall is not capable to maintain its stability against this lateral load, so what will happen? Your retaining wall gets shifted in this forward direction. No doubt there is the soil present on this side also, but as per the codal recommendation, it is recommended that the soil present on this side no doubt going to resist this lateral load, but we have to ignore this resisting force. We have to consider only the weight of the retaining wall as a resisting intensity to this applied load. So this lateral load will become a cause of lateral stability, means the retaining wall is going to be shifted in this direction. So what is the lateral load? So we already have calculated the lateral load as a sliding force I am going to call. So it is 69.95 kilonewton. In our table we already have calculated this value 69.95. Here lateral load 69.95 kilonewton. And next, what is the resisting force? Means how the retaining wall can maintain its stability against this lateral load. So it is what the weight going to be concentrated in gravitational direction. So that we already have calculated here in the table only. 205.49 is the weight concentrated in gravitational direction. The summation of this W1, W2, W3 and W4, this is the weight in gravitational direction, which is what resisting this lateral load. These all gravitational directional loads maintaining the stability of retaining wall against the shifting. If your gravitational weight is not sufficient to resist this lateral load, so what will happen? Your retaining wall gets shifted in forward direction, as you can see here in this figure. So from its actual position it gets shifted in this direction, and this is called as failure against the sliding. So we have to make our retaining wall safe against the sliding. So lateral load we have calculated as 69.95. Now the total weight is what? 205.49 kilonewton. But the resisting factor or coefficient we have to multiply with your actual gravitational load. So resisting coefficient, frictional coefficient as given in your problem statement, as you can see here, we are going to calculate the factor of safety against the sliding. So that will be equal to, as usual, zero point 0.9 times the resisting force divided by the lateral force. So zero point 0.9 times resisting force we have calculated 123.3 divided by the lateral force 69.25. After doing this calculation, we are getting the value of factor of safety against the sliding as equal to 1.59, which is greater than 1.4. Hence, I can say that our proportioned retaining wall is safe against the sliding. Now, after overall stability checks for the retaining wall, we are going to do the design for the retaining wall. So the design of the retaining wall is going to be done in three parts. In the first part, we are going to design the toe of your base slab. In the second part, we are going to design heel of your base slab. And in the third part, we are going to design the stem of the retaining wall. So here in the design steps, firstly, we are going to say design of the toe slab. So have a look over the description. The load considered for the design of the toe slab are shown in the figure. So what stresses to be considered for the designing of the toe slab, for the designing of the heel slab are given in your figure 3. So when you are going to see here, the net pressure is obtained by reducing the pressure due to the self weight of the toe slab, that is nothing but kilonewton per meter square. How this value is coming, we will see it later, from the gross pressure at the base. So concept is very simple, as your retaining wall is overall going to rest over the soil. So due to the action of the loading, your soil is going to give the reaction at the base of your retaining wall. So this upward soil pressure will be there, and some stresses are coming from the above. So we need to find out the net pressure, and for that net pressure it may be positive, means in downward direction, or it may be negative, means in upward direction. So that we have to calculate, and for that we have to design our base of the retaining wall. Especially here we are going to talk about the toe slab. So how to do this calculation? So we already have calculated in previous step as the maximum pressure on this side and minimum pressure on this side, which is 66 and 59 kilonewton per meter square. So here for the toe portion, this much is only the toe portion. So this toe portion we need to calculate the net pressure. So how you can calculate this? So here basically upward pressure is 66 kilonewton per meter square, and downward pressure will be including the self weight of the toe part of this base, and second the soil mass present on this side. But as per the codal recommendation, the soil present on this side is neglected. So that's why the weight is going to be imposed in downward direction. Due to the soil we are not going to consider, as these things we have done in our previous calculation also. We are not considering the soil present on this side. So only the self weight of this toe part of the base needed to consider. And how that is to be calculated? It's very simple. The density of the concrete as 25 multiplied with the thickness of this concrete, that is what, 0.4 meter, as you can see from here. So after multiplication of this, pressure due to the self weight of the toe slab, 25 multiplied by 0.4, it is coming out to be 10 kilonewton per meter square. So it is in downward direction, and upward direction pressure is what, 66. So 66 minus 10, it is going to become 56, which is actually present here as what, 56. Now the question is to calculate the pressure at this edge, at this point. So the pressure is actually present here. So how you can calculate this total height? Then if you are getting this total height, then you can subtract 10 from this total height. So you will come to know what is the pressure. So here the pressure is coming out to be 53.45. But how this value is coming, that is the question. How you can calculate this? So it's very simple, as we are going to consider this 66, okay, and this is the 59. Now we have to focus on this triangle. So 66 minus 59, what is going to become? It is going to become only the 7, which is given here. Next we need to know this first height Z1, because this height we are knowing as 59 very well. Now this Z1 we need to know. So how you can calculate this Z1? It is very simple. That is what, total triangle you have to consider, then on this, then this triangle you have to consider. So firstly I am going to say this is a small triangle. I am going to call it to small triangle. So small triangle Z1 divided by small triangle height as Z1, small triangle base 1.7 plus 0.4, it is going to become 2.1, will equal to big triangle height. Big triangle height is 7 divided by big triangle base is nothing but 3.3. So that is going to become what, 3.3. Now this 2.1 is taken on that side, 2.1. So we will calculate Z1 here. That calculation is given by the similarity of triangle. So after doing this calculation, we are getting the value of Z1 as 4.45 kilonewton per meter square. Now this 59 plus 4.45, what this value is coming? 63.45. Overall height is going to become 63.45 in upward direction, and the weight of the toe is in downward direction as 10. So 63.45 minus 10, we are getting the resultant pressure as 53.45. 63.45 minus 10, it is going to become 53.45. So this is the value we are getting, and the same calculations are needed to do on this side also for the portion of the hill. How to do this? It's very simple. You have to calculate the Z2 in the same way by the similarity of the triangle, and thereafter you have to subtract it from the downward pressure. Downward pressure for the portion of the hill. How you can calculate this? It is nothing but the weight of the soil, then self weight of the toe. So how to do this calculation overall, we will discuss at the time when we are going to design the hill slab. As of now, our concern is to design the toe slab. So for the portion of the toe slab, the upward net pressure is 56 and 53.45. So for that, we are going to do the calculation. So here I am going to assume the clear cover for the toe slab as 75 mm, and the diameter of bar to be used for the toe slab I am going to consider as 12 mm. Now effective depth of the footing means the base of the retaining wall, as what we are going to consider effective depth. Overall depth of the base is 400 mm minus clear cover 75 minus half of your diameter of the bar you are going to provide. So we are getting the effective depth of the base as 319 in mm. Thereafter, what, using the load factor, as all this calculation we have done on a service side, means there is no any factor we have considered over the load. But when you come to do the design, you have to multiply the your values with 1.5 for the purpose of designing. So using the load factor of 1.5, the design shear force at a distance of d 319 mm from the face of the stem. So from the face of the stem, so this is the face of the stem. From the face of the stem, what shear force is going to be developed at a distance of d, that is called as what? One way shear check, I can say. So here we are going to do the calculation for the shear force. So that is 1.5 factor value multiplication of 56 upward pressure plus 53.45 upward pressure divided by 2. So we are getting the averaging pressure on this side. Resultant pressure upward direction 56 plus 53.45 divided by 2, and that is going to be multiplied with total width of the toe is 1.2 minus d. D from the face of this stem. So d is what? 319. So you have to put the value of 319 means 0.319. After doing this calculation, the pressure value, sorry, the shear force value, we are getting 72.32 kilonewton per running meter. It is what? Previously this was the pressure, kilonewton per meter square. We are going to multiply it over the width of the base. This value is going to be multiplied with the width of the base. So this meter and this meter is going to be cancelled. Now it is going to become kilonewton per running meter of your retaining wall. So this is what? Shear force. So nominal shear we have to calculate here. Nominal shear is total shear force divided by B into D. So total shear force 72.39 multiplied by 10 raised to 3 divided by over the 1 meter length of the retaining wall. Because try to understand all the calculation and all the design for the retaining wall we are going to do over the 1 meter. Because what is the total length of the retaining wall, it is not given in your problem statement. It may be of 200 meters, it may be 500 meters, it may be 1 kilometer length of the retaining wall. So that is not defined. That's why we are doing this calculation by considering the 1 meter length of the retaining wall. So for 1 meter only we are going to do the calculation. So that's why it is 72.32 kilonewton per running meter length of the retaining wall. So shear force divided by B over a 1 meter, multiplied by effective depth. After doing this calculation, we will come to know the nominal shear as 0.23 Newton per mm square, or you can say MPa. This is what nominal shear. What shear is going to be developed in the base calculating of nominal shear stress? We are going to find out the bending moment at the face of the stem for the purpose of designing of toe slab. So basically, if you are going to see, so we are going to calculate the bending moment at this phase. So for the purpose of designing of this toe slab, it is very important to calculate the bending moment at this, because unless you are not calculating the bending moment, so you cannot able to find out the what reinforcements are required to provide in this phase. So where the main reinforcement is needed to provide for the base of the retaining wall, we need to understand the flexural response of the retaining wall under the application of the loading. So when the load is going to act in this lateral direction from the soil, and there is a upward soil pressure from the soil at the base of the retaining wall, the flexural response of the retaining wall will be of this shape. So actually, due to these lateral loads coming from the soil, your stem is going to be deflected in this shape. So this is called as flexural response of your stem. And as you have seen, the maximum upward soil pressure is formed on this side. There is what maximum soil pressure in upward direction is here, and here the minimum soil pressure. So this part, due to the more upward soil pressure, is what lifted. So flexural response of this toe portion is in this form, so that the bottom face is under tension and top face is under the compression, and the face which is under tension, we need to provide the main reinforcement in that on that face. Likewise, when you are going to see this portion, so what is happening here, what actually the top face is under tension and bottom face is under the compression. So main reinforcement needed to provide here on the top. Getting? So for the heel, main reinforcement needed to provide on the top, and for the toe, the main reinforcement needed to provide at the bottom. So for that, we need to do the calculation for the movement at the face of the stem uh, for the designing of the toe. And when you are going to design the heel, we need to calculate the movement at this face. So firstly, we are going to do the calculation for the toe. So here, what movement? So we are having the net soil pressure distribution. So on this side it is 56, and on this side it is 53.45 kilonewton per meter square over a meter of length of the retaining wall, because all the calculation we are going to do over the 1 meter length of the retaining wall. So here, firstly we are going to multiply it with 1.5 as the factor value, because we are going to do the design. So the service value should be multiplied with the 1.5 to get the ultimate load or ultimate movement. Okay, thereafter we have to calculate the movements. So this area is going to be divided into two areas. One is your rectangular one and another one is your triangular one. So for this rectangular one, we have to calculate the area, and that area to be multiplied with the perpendicular distance to its aerial centroid. So simple calculation will be 53.45, because the height and the base is what 1.2, the width of the toe is 1.2. So 53.45 multiplied by 1.2 is going to become area. This height 53 and this base is 1.2 is going to become area. Then half of this 1.2, half of this, it is going to become 1.2 divided by 2. So basically 53.45 multiplied by 1.2. Okay, this is the area to be multiplied with 1.2 divided by 2. So 1.2 is going to become square, and this divided by 2. So this is the formula we are getting the movement for this rectangular area. Now we have to do the calculation for the movement for this triangular area. So triangular area means what? 1 by 2 base into height. So 1 by 2 base is actually what? This one 1.2 and height is this one. So this will be what? 56 minus 53.45. 56 minus 53.45. Okay. So we are getting this total overall area and to be multiplied with the centroid point of this triangle. So from this corner point we have to come to the centroid point. So it is 2h by 3. So this is the what base. So 1 2 by 3 2h by 3. So this is nothing but your height. This is the base is going to become height if you are going to measure from this point. So 1 2 by 3 of 1.2. So we are finally, after doing all this calculation, we will come to know the moment at the face of the stem for the toe design is 59.56 kilonewton over a 1 meter length of the wall. Now you have to put this moment in this formula for calculating the reinforcement required. So after putting ultimate moment and all the values, characteristic strain over the 1 meter width of the retaining wall and effective depth, after doing all this calculation, we will come to know the total area of the reinforcement required as a main reinforcement on the tension face for the toe is 442 square. But we have to compare this requirement with the minimum requirement. So minimum reinforcement requirement is what? 0.12% of B into D. So after doing this calculation, it is coming out to be 480 square. So 442 is the required design required and minimum requirement is 480. So obviously we have to provide at least minimum area of the reinforcement required. So I would like to provide 12 diameter of bar. So unit area of 12 diameter of bar is going to become 113.1 square. So unit area divided by total area, this provision we are going to made over the 1 meter span. Over the 1 meter means 1000 So spacing required for the reinforcement is 235.62. But as you know, for the safety we are going to provide the spacing as 200 center to center. So finally 12 diameter of bar at a spacing of 200 center to center, the bottom face of the toe slab. As we have seen, the reinforcement is needed to provide at the bottom face of the toe slab as the main reinforcement. So hope that you all understood how to find out the reinforcement at the bottom face of the toe slab. Now finally we would like to find out what is the total reinforcement has provided after reducing the spacing. Total area of the reinforcement provided as unit area divided by final reduced spacing as 200 or a 1 meter span. So we have provided 565.5 square area of the reinforcement, and actually minimum required was 480. We are going to provide 565. So that is what safer one. And in percentage if you are going to calculate it, so it is going to become 0.177 percentage of reinforcement we have provided. So finally we would like to calculate critical shear resisting capacity. So as we already have calculated the nominal shear as 0.23, so we have to compare nominal shear and the critical shear after calculating. So if your nominal shear is less than of your critical shear, then we will say that our design is safe for the shear. And if you are getting your nominal shear more than of your critical shear, then we will say that it is needed to revise the design. So simple approach is that we have to calculate the finally provided percentage of reinforcement, which is 0.177. So as per our IS 456 2000 page number 73 and table number 19, if you are going to see that IS 456 2000 table number 19, so here our provided percentage of reinforcement is 0.177. So it is in between of 0.15 and 0.25. And for 0.15 for M25 grade of concrete, the critical shear is 0.25 and for 0.29, and for 0.25 for M25 grade of concrete, the critical shear is 0.36. Now in between our value is what? 0.17. So for 0.17 we need to do the linear interpolation, and after doing this linear interpolation you will come to know what is the critical capacity. So after the linear interpolation we are getting the critical capacity 0.304, and your nominal shear is what? Nominal shear is 0.23. So 0.23 is less than of your critical capacity, hence it is safe for shear. So finally now I am going to find out the distribution reinforcement, the reinforcement in distribution direction. So it is again minimum reinforcement we are going to provide 0.12% of the width. Consider 1 meter, overall depth as 400. So minimum reinforcement is what? 480 mm square required for the distribution reinforcement. So for distribution we are going to provide 10 mm diameter of bar. So unit area of 10 mm diameter of bar is 78.5. So spacing requirement we need to calculate spacing requirement. So unit area divided by total area required over a 1 meter, it is 163.5 in mm. So we are going to provide as value 150 mm center to center distance between the distribution reinforcement. Got it? So finally we are going to write here as provide distributors or distribution reinforcement as 10 mm diameter of bar at a spacing of 150 mm center to center. So actually minimum requirement was 480. We have reduced the spacing. So now finally provided reinforcement is what? 78 unit area, 78.5 divided by spacing finally provided over a 1 meter. So 523 mm square area of the reinforcement we have provided. Now I want to calculate it in percentage. So percentage will be what? Total area finally provided divided by sectional size. So 523 divided by 1 meter 1000 mm, 319 here it is written, or you can write as effective depth also you can take. So as of now here it is taken as what? Effective depth. Both are okay. There will be slight change, so acceptable. 319. So after doing this calculation we will come to know 0.163 percentage, which is greater than of your minimum percentage of reinforcement. So now here it is also what? Safe. So we have provided the main reinforcement along this direction, main reinforcement, and distribution reinforcement as 10 mm dia at a spacing of 150 mm center to center. So in this way we have completed the design of your toe slab. Hope that you all understood how to do the design of toe slab. Now next we are going to design the hill slab. Let's start the design of the hill slab, and for the purpose of designing of the hill slab we have to follow the same procedure as we have done for your toe slab. So first of all we need to calculate the net pressure that is going to develop at the hill slab of the base of your retaining wall. So for that the calculation we already have done for the toe portion, and now we have to look at for the portion of the hill. So as we earlier have discussed that the this portion is going to be called as toe slab, this portion is going to be called as hill slab. So we are going to talk about the hill slab. So total intensity of the pressure going to be directing in downward direction, means over the soil, and there will be what? Resultant pressure from the soil to the base of your retaining wall. So calculation is needed to do. So what intensity of the pressure is going to be directing in downward direction? It is the calculation or summation of the pressure going to be imposed by your soil present on this side and the self weight of the hill slab. These two addition will give you final pressure is directing in downward direction. So the calculation is going to be done here. As you can see, due to the soil, the intensity or the unit weight of the soil is 19 kilonewton per meter cube, and the height of the soil above the base of the retaining wall is 4.3 meter. If you are going to see the retaining wall, so it is height above the base which is having the soil is 4.3 meter. So that is going to be calculated or considered in your calculation. So 4.3 19 into 4.3, that is going to become 81.7 kilonewton per meter square is directing in downward direction plus self weight of the hill slab. Self weight of the hill slab can be calculated by multiplying the unit weight of the concrete with a thickness of your hill slab, that is 400 mm. It is going to become 0.4 meter. After doing this, we are getting the value of 10 kilonewton per meter square. You have to add these two value. You will get finally total intensity of the load directing in downward direction, that is 91.7 kilonewton per meter square. But you know very well the upward soil pressure we already have calculated in this figure. So on this side the total upward soil pressure is 59, and here ordinate we already have calculated 62.61 kilonewton per meter square. So the resultant or net pressure at this two section means at the face of the stem and at the edge of the hill. So for these two sections we need to calculate the net pressure. So that's very simple. It is in downward direction 91.7 and it is 63.45 in upward direction. Okay, so the resultant will obviously be in downward direction. If you are going to take the difference 91.7 minus 63.45, so what value you will get? Here it is given, this value will be what? In downward direction 29.09. And next if you are going to subtract the downward value 91.7 minus 59 in upward direction 59, so the resultant value will be in downward direction because 91.7 is greater, which is in downward direction. So the resultant value will be what? 32.7. This difference will be what? 32.7 kilonewton per meter square. Both the values are in downward direction. So the net pressure acting in downward direction ranging between 29.09 kilonewton per meter square, 32.7 kilonewton per meter square as shown in the figure 3. In this figure 3 mainly we have done all this calculation for the pressure. Now we have to calculate the what shear force is going to be developed at the face of the stem. When you are going to see here, I am going to do the calculation at this face what shear force is going to be developed. So the calculation will be very much simple. That is what? 1.5 is the factor value. We want to calculate the ultimate value. That's why factor is 1.5. Multiplication with average of these two pressures. That is what? 29.09 plus 32.7 divided by 2. It is to be multiplied over the span of your hill slab. So span of this hill slab is 1.7 meter. So after doing this calculation, we are getting the value as 78.8 kilonewton over a running meter of your retaining wall. This calculation has been done. Now next we would like to calculate the nominal shear stress. Due to this shear force, what shear stress is going to be developed at the face of your retaining wall, at the face of the stem of your retaining wall? What nominal shear stress is going to be developed at this face? We are going to do the calculation. Okay, so basically it is a vu divided by b into d. So b over 1 meter we are doing the calculation, so 1319, and vu means ultimate load 78.8 into 10 raised to 3 in newton we are going to convert it. So finally we are getting the nominal shear 0.25 newton per mm square, or you can call it to as MPa. So this is all done for the calculation of the shear force and nominal shear stress. Now after finding out the nominal shear stress for the hill slab, we are going to find out the ultimate moment for the hill slab, and with this ultimate moment we are going to find out the flexural reinforcement required for the hill slab. So for that reason, what to do? We need to find out the moment at the face of the stem on the side of the soil, on the side of the backfill. The stem face is there, and at this stem face we are going to calculate the moment by considering this complete span of the hill slab, that is nothing but 1.7 meter. So for calculating the moment we are going to take the help of stress distribution diagram. This is your stress distribution diagram. We are going to take the help of this to find out the moment. So as you can see, what this total area of trapezoidal we are going to divide into two parts. One is your rectangular part, another one is your triangular part. So the moment calculation will be what? Area of this rectangular portion going to be multiplied with the centroidal point distance measured from the stem face. So this is going to become the moment. So here 29.09 multiplied with the width of your hill slab, that is 1.7. This overall going to be multiplied with half of this width, that is 1.7 divided by 2. So this 1.7 is going to become square divided by 2 multiplied by 29.09. So this all terms is actually present here. Thereafter next area or next item is your triangle. So triangle area, you know, half base means this is 1.7, and height, the difference of 32.7 minus 29.09. So this value is overall actually present here, going to be multiplied with centroidal distance of this triangular area. So that is going to become somewhere here, and that is at a distance of 2h by 3. Means this is what the height, this is what the height or base, whatever you are going to call. So you can call it to as 2 base by 3. So this is 1.7. So 1.7 2 by 3. After doing this all calculation with the multiplication of 1.5, we are getting the moment for which we have to design our hill slab as 68.27. Now finally this value you have to put in this formula along with all other values as width 1 meter, depth 319 square, again 1319. After doing this calculation we will come to know the reinforcement required for the hill slab as 508.43 mm square. Now we have to compare this demand of the reinforcement with your minimum reinforcement demand. So after calculating the minimum reinforcement demand, we will come to know 480 mm square. Minimum area of the reinforcement required as what? 480, as similar to that of our previous case. So now we have to compare with the demanded reinforcement, that is 508. So after comparison we will come to know that 480 is less than of 508. So we have to provide at least the greater value. 508.43 is the reinforcement we are going to provide. Finally, now using 12 mm diameter of bar, and the unit area of 12 mm diameter of bar is what? 113.1. Now I would like to find out to a what spacing I have to provide the reinforcement in the hill slab. So for that reason, what I need to do? I need to do this calculation. Unit area of 12 mm diameter of bar divided by total area of the reinforcement you are going to provide over a 1 meter span. So the spacing required to provide as 222, but normally we are providing the spacing in a round of 25 mm. So we are going to 200 mm center to center spacing. So 12 mm diameter of bar at 200 mm center to center on the top face of the hill slab, we are going to provide the main reinforcement. Now finally reinforcement which is provided, because the demand of the spacing was 222, we have reduced it to 200, means the reinforcement are going to become closer, spacing is going to be what? Reduced. So the bars are going to become closer, so reinforcement is going to increase. So now unit area divided by finally provided spacing over a 1 meter, now giving the finally provided area of the reinforcement as 565. Earlier demanded area of the reinforcement was 508. Now by reducing the spacing, area is going to increase 565.5 mm square, which is greater, that is safe. In percentage, if suppose you want to calculate it, so area of steel divided by B into D. After doing this calculation we will come to know in percentage this reinforcement is in the section of the hill slab as 0.177 percentage. The area of reinforcement is there in percentage. Okay, now we have to ensure that whatever the shear stress has been developed as 0.25 MPa, whether it is going to become a cause of failure of your base of the retaining wall, that is the hill, due to the shear or not. So we have to find out critical capacity of my section, critical capacity of my hill slab. So provided percentage of reinforcement is what? 0.177, and grade of concrete is M25. Okay, 25 grade of concrete is there. So we have to use IS 456 page number 73 table number 19 if you are going to find out the percentage 0.15, so for that, for M25 grade of concrete, the value is 0.29. For 0.25, the value is 0.36. Our percentage of reinforcement as provided as what? 0.177. For that, we have to find out the value. So by doing the linear interpolation, you will come to know the value is what? Critical capacity of your hill slab for resisting the shear is 0.3089. Now you have to compare it with your calculated value of shear as 0.25. It is what? 0.25. So we are going to compare it with this. So it is not 0.22, it is 0.25. So even this 0.25 value is less than of 0.3. So you are safe in shear. Your design means the section of your hill slab in respect of its depth and provided percentage of reinforcement is safe for resisting the shear stresses. Okay. Now finally the main reinforcement we have decided. Thereafter we are going to do the calculation for the distribution reinforcement. So distribution reinforcement, again, minimum percentage as 0.12% of B into overall depth. So here the calculation is giving 480 mm square per meter length of your retaining wall. So now I would like to provide 10 mm diameter of bar as a distribution reinforcement. So 78.5 is the unit area of 10 mm diameter of bar. Now what spacing is required? So spacing will equal to 78 unit area divided by total area 480 over a 1 meter span. 163.5 mm spacing is required to provide. Hence we are going to provide the spacing as 150 mm center to center. Finally distribution reinforcement, we are going to provide 10 mm dia at a spacing of 150 mm center to center. So finally provided area of the reinforcement will be what? As that of your main reinforcement. What we did after finalizing the spacing, again we are calculating finally provided area of the reinforcement. So unit area divided by finally provided spacing over a 1 meter span. Now 523, demand was 480, we are going to provide 523. So it is again safe, provided reinforcement little bit more than that of the minimum demand of the reinforcement. Now in percentage we would like to calculate it. So in percentage it is total area divided by B into D. Total area 523 divided by 1000 multiplied by 319. After doing this calculation, the provided area of the reinforcement as a distribution reinforcement as 0.164%, which is greater than of your 0.12%. Minimum requirement of the reinforcement was what? 0.12% was there. We have provided a 0.164% of reinforcement. So in this way we have completed the design of your hill slab, and we earlier have designed our toe slab. So both toe and hill slab we have successfully designed here. Now the next component part of your retaining wall we have to design as your stem. Now we are going to discuss the design of the most important component part of your retaining wall, that is nothing but your vertical stem. So if you are going to see the figure, so as you can understand from the figure that the soil is going to act laterally over your vertical stem, and due to this action your vertical stem is going to be deformed in this pattern. So as you can see, due to the action of this lateral force on the vertical stem, your vertical stem is going to be deflected in this direction or in this pattern. So this face will be under tensile stress and this face will be under the compressive stress. So overall, due to this lateral force from the soil at the base of your vertical stem, the maximum movement is going to be generated. The maximum movement is going to be developed at the base of your cantilever portion of your retaining wall. So we basically have to calculate the how much movement is going to be developed at the base of your cantilever portion, and for that movement we are going to provide the reinforcement, that is nothing but your flexural reinforcement. So these all calculations we are going to do in our step. So firstly we are going to write here as height of the cantilever portion of your stem. So if you are going to see, our height of the stem is 4.3 meter. Now we are going to assume the clear cover as 50 mm for the vertical stem and the diameter of bar to be as 12 mm. We have not designed the reinforcement, but at the early stage we are deciding the preliminary diameter of the bar needed to provide as 12 mm. If suppose you want, you can consider it as 16 mm, 20 mm, your choice. But as of now I am going to consider as what, 12 mm. Thereafter, effective depth at D at the base of the stem. So when you are going to see the figure, so in this figure, if you are going to see at the base, so at the base we have considered the width or thickness of this vertical stem at the base as 400 mm, and on the top it is 225 mm. So we basically going to calculate the moment at the bottom, and we are going to design the reinforcement for the bottom face, and that same reinforcement we are going to extend over all the height of the cantilever portion. So that's why we are going to consider the width or thickness at this section, that is nothing but 400. So overall thickness is 400 or overall depth is suppose 400. So what to do, just come to calculation and see 400 minus clear cover as 50 minus half of your diameter of the bar that you have assumed. So it is 344 in mm. Now, force due to active earth pressure. Earlier I have explained that due to this lateral force of the soil, the pressure is going to act on your cantilever portion, and that is nothing but again similar to that of what, the area of this triangular stress. Okay, so 1 by 2 base is nothing but your coefficient of active earth pressure multiplied by density of your soil multiplied by height of your stem. This is the base and this is the height. Okay, so what again the height you have to consider. So I'm going to write here as 1 by 2 Ka, density of your soil multiplied by h. Again you have to multiply with the height as h, so that is going to become h square. So 1 by 2, this value we are getting, and the total height of the stem we are having as 4.3 meter. You have to put all the values here. After putting all the values here, we will come to know the value of this PA as 58 kilonewton per running meter of your retaining wall. Okay, now bending moment we have to calculate. So bending moment, how you can calculate it? It is very simple. You have to multiply this lateral force, you have to multiply with the perpendicular distance from its base. It is what, very simple, and this lateral force is going to act at the CG of this triangle. Okay, and that comes at a distance of what, if you are going to measure it from here, it is going to become h by 3, and if you are coming from the top, from the angle side it is going to become 2h by 3. This is what the consideration, right? So here h by 3 only will be, because we are going to consider it from the base. So coming back to the discussion here in the calculation, so pa and h by 3 and this 1.5 is just to get the ultimate value, ultimate moment. So if you are going to do this calculation, we will come to know the bending moment as 125 kilonewton meter per meter of the length of your retaining wall. It is not kilonewton only, it is kilonewton meter over the 1 meter length of the retaining wall. This correction I will do in the file. Now, after all of this, the next we have to calculate what reinforcement required at the base of the cantilever portion. So the formula you have to put here, all the values you have to put here, and after giving all the values here, we will come to know the reinforcement required to provide for this flexural design for the vertical stem as 880.9 mm square. This much area of the reinforcement is needed to provide. So I would like to provide 12 mm diameter of bar. So unit area of 12 mm diameter of bar is what? 113.09. If I am going to put this value, unit area divided by total area in demand over a 1 meter, because this reinforcement or these overall calculations we have done over the 1 meter length of the retaining wall. So this is over the 1 meter, this unit area divided by total area demand or you have to multiply it with a 1 meter length of the retaining wall, that is 1000 mm. After doing this calculation, we will come to know that 128 mm spacing is required between the reinforcement. Okay, hence we are going to provide as spacing as 100 mm center to center. So finally provide the flexural reinforcement in a vertical stem. If you are going to see in a vertical stem, the reinforcement to be provided along the height as what 12 mm diameter of bar at a spacing of 100 mm center to center, and these bars into shear keys as shown in the figure. Okay, that is not applicable here. Now finally I would like to find out what is the total reinforcement has been provided. So actually demand was 128 mm spacing. We have reduced the spacing, means if you are going to reduce the spacing means area of the reinforcements are going to increase. So the reverse calculation we are going to do, unit area finally provided spacing over a 1 meter, we will come to know finally provided area of the reinforcement in the vertical stem is what 1130.97 mm square. This much area of the reinforcement we are going to provide in a vertical stem. Now PT finally provided percentage of reinforcement in your vertical stem, that is what total area of the reinforcement provided divided by section size and by the percentage, that's why 100. So after doing this calculation we will come to know that total percentage of reinforcement provided in the vertical stem as 0.328 percentage. Now after the flexural design of cantilever portion of the retaining wall, we are going to do the check for the shear, whether it is needed to design this cantilever portion of the retaining wall for the shear or not. For that purpose, we are going to consider a critical section at a distance of d from the base of the retaining wall cantilever portion. So effective depth is 344 as we earlier have calculated. If you are going to see here, we already have calculated effective depth at the base of the stem. So when you are going to see the figure, so we were considered full width or thickness at the base of this cantilever portion is 400, and we have calculated the effective depth. So that effective depth is actually 344. So we are going to consider the critical section at a distance of d from the bottom of your cantilever portion. So from this base at a distance of d, we are considering the critical section for the shear. So if you are going to measure it from the base up to this level, so I am going to measure the total height from the top. The remaining height is actually 3956. Okay, this is the height. So we have to calculate the shear force, and the shear force is going to be calculated by considering this area. Okay, this triangle area, that is half of base, this base and this total height. So the base will be Ka, coefficient of active earth pressure, multiplied by density of the soil, multiplied by what, the height. Okay, this height, that is nothing but z, and this completely going to be multiplied with the total height as z again. So it is going to become Ka gamma s, means density of the soil, multiplied by z square, and as it is the area, so half. Okay, so triangle area, half base into height. So this same value is actually written here. If you are going to see Ka, that is what coefficient of active earth pressure 0.33, density of the your soil 19, and z value is nothing but your 3.956 square divided by 2. So after doing this calculation, we will come to know the shear force as 74 kilonewton. This is what, kilonewton over a 1 meter length of the retaining wall. This calculation is going to be done over the 1 meter length of the retaining wall. So I would like to calculate at this section, at this critical section for the shear, what shear stress, nominal shear stress is going to be developed due to the stress, due to this lateral stress from the soil. So nominal shear stress will equal to your force value divided by B, means consider width of the retaining wall for which you are going to design. So we are going to design for a unit width 1000 effective depth 344 at the base of the vertical stem. So after doing this calculation, we will come to know nominal shear stress as 0.22 MPa, or you can say Newton per mm square. Now, this is the stress due to the action. Now, what is the capacity at this section? If you are going to calculate what is the capacity to resist the shear at this section for this cantilever portion of the retaining wall. So, I need to do that calculation. So, two things are actually present here. One is your concrete, another one is your reinforcement. These two things is going to make the capacity to resist the shear. So that calculation is going to be done here. So the percentage of reinforcement provided at that section. So percentage of reinforcement is provided as 0.328. We earlier have calculated total reinforcement is provided in the vertical stem. So we have calculated total reinforcement is provided 12 mm diameter of bar at a spacing of 100 mm center to center. After calculating by the percentage, we are getting as 0.328. Okay, so this percentage of reinforcement is present there, and grade of concrete is what? 25. As I earlier said that at this section two things are present. One is your concrete, another one is your steel. Both combinedly going to resist the shear stress. So due to presence of concrete and steel, what is the capacity at this section? I need to calculate that. So here, for if you are going to look at as for 562,000, page number 73, table number 19. So when you are going to see table number 19, let me show you. For M25 grade of concrete, and as our percentage of reinforcement is 0.328, it comes in between 0.25 and 0.5. When you are going to see 0.25 and 0.5, in between our value is coming. So for 0.25, the M25, the value is 0.36, and for 0.5 it is 0.49. So when you are going to see here 0.25, 0.36, 0.5, 0.49. Now our intention is to calculate the value tau c for 0.328. So after doing this calculation, we will come to know that the critical shear capacity is 0.4 MPa. When you are going to do the linear interpolation, so after doing the linear interpolation, you will come to know the value of tau c as 0.4 MPa. Now nominal shear stress as 0.22, which is less than of critical capacity 0.4. Hence, it is safe for the shear. Now, finally, whatever the shear stress is going to be developed at that section, which is less than of your capacity is more and the stress is less. So now you are safe for the shear. Now, finally, the distribution reinforcement we are going to provide. Okay, so again, the distribution reinforcement like 0.12% of B into D overall depth here it is considered. So after doing this calculation, we will come to know 480 mm square per meter length of the retaining wall. So I would like to provide 10 mm diameter of bar. Okay, so unit area of 10 mm diameter of bar is 78.5 mm square. Now unit area divided by total area in demand multiplied by considered width of the design. So it is 163. We are going to provide the spacing as 150 mm center to center as a distribution reinforcement. Now finally, providing distribution reinforcement as 10 mm diameter of bar at a spacing of 150 mm center to center, right, throughout the height of your cantilever portion of your retaining wall. Now finally, ST provided as a distribution reinforcement 78.5 unit area divided by finally provided spacing, and this is giving the area of the reinforcement as provided 523 mm square. Now finally, percentage of reinforcement for the distribution bars, it is 0.15%, which is greater than of your 0.12% as minimum required, hence it is safe. Minimum requirement is what? 0.12%. We have provided it as what? 0.15%. So in this way, we have completed the design of the cantilever retaining wall. We have completed the design for the base of the retaining wall. We have designed the cantilever portion of the retaining wall. In this way, we have completed the design of the cantilever retaining wall manually. Now, finally, let me summarize the complete design. So, firstly, we have seen the problem statement. Thereafter, we were decided the section sizes of the component parts of your retaining wall. Thereafter, we were calculated the forces and moments by using the tabulated form. Thereafter, we were performed the stability checks against the overturning, against the bearing pressure. Thereafter, we have performed the stability checks against the sliding, and we were found that our design means the proportioning of the section size of the cantilever retaining wall is safe. Thereafter, we were design the toe slab of your retaining wall, and thereafter we have calculated the main reinforcement at the bottom of the toe slab. Thereafter, distribution reinforcement we have calculated. In the same manner, we were design the heel slab and calculated the flexural reinforcement as the main reinforcement. Thereafter, distribution reinforcement. So, in this way, we have completed the design of the base slab of your cantilever retaining wall. Thereafter, we have designed the vertical stem, okay, cantilever portion, and we will come to know that the reinforcement, what reinforcement is actually needed to provide as the main reinforcement. Thereafter, we have calculated the distribution reinforcement. In this way, we have completed the design. Now we have to prepare the schedule and detail in respect of these design results. So whatever the results we got, that all results we have to write in a tabulated form. So for the vertical stem, we are having the two phases. Okay, two phases we are actually having. One phase towards the earth side and the one phase other side of the earth side. So what reinforcement needed to provide on this side, what reinforcement is needed to provide on this side, that we need to understand. Okay, so here on the earth phase, two conditions are there. One is your continuous reinforcement, another one is your curtailment. Let's first try to understand what does mean by the continuous, what does mean by the curtailment. So here curtailment means what? Try to understand. When we are doing the calculation, we were calculated the moment at the base of this vertical stem, and that was the maximum here. But when you move towards the top point, so the movement is going to be decreasing. Maximum movement will be at the base, and on the top the movement will be zero, and it is what increasing from top to bottom. So maximum reinforcement is required up to the half height of the cantilever portion. So whatever the reinforcement required at the base, if suppose the same reinforcement you are going to provide on the top portion also, it will be obviously a uneconomical. Okay, so for that reason, what we are going to do, whatever the reinforcement in demand, that demanded reinforcement we are going to provide to a half height. But we are going to take further safety in respect of your development length. So we are going to extend it up to the development length. So these bars which are going to cut at a particular height, it is going to called as curtailment. So for this height, okay, what we are going to do, we are going to provide the spacing as per the demand as 100 mm center to center. So when you are going to see the design for the vertical stem, okay, so for the vertical stem, design reinforcement demand was for the vertical stem 12 mm diameter of bar at 100 mm center to center. So same reinforcement here it is provided as the curtailment bars 12 mm diameter of bar at 100 mm center to center. But when you move towards the edge, top edge, so it is what going to make it as alternate. Okay, one bar is going to cut here, so there will be space, so spacing is going to become 200, 100 and 100 going to become 200. So that is actually written here 12 mm diameter of bar at 200 mm center to center. And the distribution reinforcement, we have calculated the distribution reinforcement as 10 mm diameter of bar at 150 mm center to center. So that is written here distribution reinforcement as 10 mm dia at 150 mm center to center. As you can see here, distribution reinforcement, this distribution reinforcement, these all these circles are nothing but your distribution reinforcement 10 mm diameter of bar at 150 mm center to center. So there will be no any change from bottom to top for the distribution reinforcement, only there is a change for the vertical bars. And okay, on the other side, no calculation we have performed, because we are going to provide the minimum reinforcement for the vertical as well as distribution, that is nothing but the 10 mm diameter of bar at 150 mm center to center as the minimum reinforcement on the other face. So that is written here, opposite face, no curtailment is there. Okay, continuous bar will be there, 10 mm diameter of bar at a 150 mm center to center as vertical, and distribution as 10 mm diameter at 150 mm center to center. So in this way, the schedule and detail is going to be done for your vertical stem. Now come to talk about the base. So we have designed our base in two parts. One is your toe slab, another one is your heel slab. So firstly we are going to write the reinforcement for the toe slab. So for the toe slab base, okay, top reinforcement. So for the top reinforcement here required for the hill slab. For the hill slab top reinforcement required, and for the toe slab bottom reinforcement was required. You have to understand the flexural response of your cantilever retaining wall. So as you can see, for the flexural response for the toe portion, main reinforcement required at the bottom, and for the heel portion, main reinforcement required at the top. So the same thing is actually present here in your schedule. So for the base slab, top reinforcement and bottom reinforcement. So for the top portion, we have to follow the heel slab, and for the bottom reinforcement, we have to follow the toe slab. Right? When you are going to see the calculation and the result, so we will come to know, yeah, design of the toe slab. So for the design of the toe slab, we got the reinforcement 12 mm diameter of bar at 200 mm center to center. So for the bottom, okay, because when you are going to see the bottom of the toe slab, so here bottom 12 mm diameter of bar at 200 mm center to center, main reinforcement, and distribution reinforcement for this case 10 mm diameter of bar at 150 mm center to center. So it is 10 mm diameter of bar at 150 mm center to center. So overall for the base, we are going to say bottom reinforcement is needed to provide as 12 mm diameter of bar at 200 mm center to center as the main reinforcement, and distribution reinforcement as 10 mm diameter of bar at 150 mm center to center. These dots are your distribution reinforcement. As you can see, 10 mm diameter of bar at 150 mm center to center at top and bottom both. Now top reinforcement, for the top we need to look at the hill slab design. So for the hill slab design, when you are going to see here 12 mm diameter of bar at 200 mm center to center on the top face of the hill slab. So here it is written as top 12 mm diameter of bar at 200 mm center to center, and distribution reinforcement here it is written as again 10 mm diameter of bar at 150 mm center to center, 10 mm diameter of bar at 150 mm center to center, as you can see. So complete detailing is actually present here. So vertical stem, the reinforcement we have discussed at the bottom, main reinforcement 12 mm diameter at 200, and for the top face means for the hill portion 12 at 200 mm center to center, and top and bottom distribution reinforcement 10 at 150 mm center to center. And this is what section along the length. So this is showing how the curtailment of the bars is needed to provide. So hope that you all understood the complete design of your cantilever retaining wall with its scheduling and detailing. Now by using this Excel sheet, you can do the complete design. So first of all, try to understand how to use this Excel sheet. So while using this Excel sheet, you have to edit the values in yellow cells only. In white cells, you don't need to do anything, and wherever you are getting this orange color cell, that is suggesting the safe value for that respective parameter, and these black cell values means you need to skip this area. Wherever you are getting the black cells, you have to skip that cells or that area, and wherever you are getting the red cell, that will be the sign of danger or failure. So by the color coding, you have to understand. So you have to edit the values only in yellow cells. So firstly, we would like to look at once again the problem statement. So when you are going to see the problem statement, so we have given the height as 3.7 that we have to write in our Excel sheet. So when you are going to see height above the ground level 3.7 meter, we have given unit weight of the soil is 19 kilonewton per meter cube. SBC of the soil we have given. What is the SBC? So the SBC of the soil has given as 120 kilonewton per meter square. So that we are going to define here. Thereafter, pressure due to surcharge. So as in our problem, there is what? Flat backfill. There is no any surcharge. In your problem, if suppose the surcharge is present of any particular intensity, suppose 30 kilonewton per meter square is your surcharge. So you have to put this value here. So automatically the surcharge will be defined here in this figure. So everything is going to be updated automatically. But as in our problem statement, there's no any surcharge. That's why I'm going to put it as 0. That's it. Now, friction coefficient between your soil and concrete. So that we have given as 0.6. As you can see, 0.6. So that we are going to define here as what? 0.6. Now, angle of internal friction is 30 degree as given. So that I am going to write here as 30 degree. Angle of inclination of the backfill. So as we are having our flat backfill, it is not having any inclination. For an example, you are going to deal with any of the problem where the backfill is having the angle of 45 degree. So you can put here as 45 degree. So yeah, inclination of your backfill is what? 45 degree. Here it is what? Created. Right? So as of now, there's no any inclination of your backfill. So make it to be what? 0. So this sheet is capable of designing of three types of the retaining wall. Sorry, the retaining wall with three types of the backfill. One is with a flat backfill. Another one is the flat backfill with surcharge. Okay. And third is your backfill with the inclination. Now, material property. Concrete density M25. Concrete density is 25. Concrete grade is M25 and rebar grade as AP500. If suppose you want to change it, you can change it for the grade of steel or for the grade of your concrete, you can change it as per your need, right? Thereafter, now here depth of the foundation as required. So it is suggesting the depth of the foundation means from this level to up to the foundation what depth to be adopted. So it is given as what? 0.7 meter is required. When you are going to see your manual calculation, in the manual calculation also the same demand was there as 0.7 and sheet is also recommending the same thing 0.7. So we are going to provide as 1 meter. Total height is going to become 4.7 meter. As in your manual calculation, total height is going to become what? 4.7. 400 plus 4300 is going to become 4700. So we are going to write here at 4700. Overall width of the footing. Overall width of the footing in demand is what? 3.29. So we are going to provide overall width of the footing means base of the cantilever retaining wall is 3.29 is in demand. So we are going to provide as 3.3. So it is what? It is the suggestion. As you can see here in the color code, suggestion for the safe value. So it is 3.29 is the safe value. Suggestion we are going to provide as 3.3. Thereafter, width of the hill slab. So 1.67. How much this portion, okay, needed to consider? So it is 1.65. We are going to consider as 1.7. Now, thickness of the base slab. What thickness to be considered? So the suggestion by the sheet is what? 0.39. So that's why we are going to adopt it as what? 0.4 means 400 mm. You can edit any value here. You can edit the any value here. You can take it as zero point 0.5. So accordingly, your figure is going to be adjusted. If you are going to define it as 1 meter, so accordingly, the sheet is what going to be adjusted. So as of now, we have to consider only the zero point 0.4. So that's why we are going to put it as what? 0.4. That's it. Now, stem thickness at the base. 0.3 is minimum. At the base, we are going to adopt it as what? 400 mm. So it is 0.4. We have taken on the top minimum as per the recommendation is what? 200 mm. Minimum demand we have provided 230 mm for the safety. Now assume the diameter of bar for the base slab. So we are going to adopt the diameter of bar at the base slab as 12 mm, right? And assume the clear cover for the base slab. So we are going to consider the clear cover as what? 50 mm. Okay, clear cover. Base slab and stem. So 12 mm also for the stem. Base slab and stem both, and clear cover 50 and 50 both, right? Thereafter the further calculation the sheet is going to do, all the calculation here it is going to be done. Now total force 205 kilonewton, 205.48 in your manual calculation you can see 205.49, and in your excel sheet also the same thing. Lateral force 69.95, in your manual calculation 69.95. Now next is your movement, resistive movement 443. When you are going to see, it is going to become 443 about your, okay, 443. Overturning movement 109.82. when you are going to see here, overturning movement 109.59, very closer value the calculation has been done. Now the stability checks. So safe against the overturning, safe against the sliding, no need to do, no need to provide the shear key, and safe against the bearing. It is what we are getting safe, right? If it is failing, it is going to be representing by the red cells. Okay, for an example, suppose any of the value is what? Not satisfying, then you are getting the red cell here. Okay, so that is you need to do the correction. Here you will get the red cell. uh, you need to do the correction. Here you will get the red cell. You need to do the correction in your previous calculation. So as of now we are getting all are passing green cell, right? Thereafter the designing has been done. So finally we have to look at the design for the toe slab. For the toe slab, main reinforcement moment is coming as what? 58.95. Minimum area of the reinforcement 480. I am going to provide 12 mm diameter of bar. So spacing required is coming out to be 235.62 toe slab. When you are going to see your manual calculation for the toe slab, so there was a demand of 235.62 mm, and when you are going to see the excel sheet calculation, so it is 235, obviously exactly same. So I am going to provide as 200. So finally the reinforcement we are going to provide as 12 mm diameter of bar at a spacing of 200 mm center to center. Distribution reinforcement 10 mm diameter of bar, spacing required as 163. So we are going to provide as 150 mm center to center, right? So for the toe slab, the shear check performance has been done. Here 0.3 critical capacity. Okay, so we are safe. If it is not passing, suppose I am going to provide the lower reinforcement. Suppose I am going to provide the spacing as the demand is 235. You are not allowed to provide the spacing more than of this 235. Suppose I am going to provide 250. So as per the demand, we are going to provide the less reinforcement. Okay, so here it is what? Provided percentage of reinforcement 0.13. Okay, so your capacity, shear resisting capacity is 0.27. Still it is safe because nominal shear stress is what? 0.22 and zero point 0.2. So you are safe. Now again I am going to provide as 300. It still it is safe. Suppose I am going to provide as 500 for an example. Now it is failing. Your shear resisting capacity is 0.2 and your stress is 0.22 and zero point 0.2. So you are failing. Okay, that's why the demand is what? 235. I am going to provide as 200, right? So it is safe. Thereafter hill slab. For the hill slab, the reinforcement demand uh, is 480. Minimum demand is also 480. So 12 mm diameter of bar at 235. Again we are going to provide 200 mm center to center. So percentage of reinforcement 0.16. Again it is safe for the shear. Now vertical stem, vertical portion of the retaining wall. So 125 kilonewton meter the moment is there. If you are going to do, if you are going to see your manual calculation, so it was a movement as about to 125 kilonewton over a 1 meter length of the retaining wall. So when you are going to see your spreadsheet, same calculation is coming, and the reinforcement demand 887. If suppose I am going to provide 12 mm diameter of bar, 120 mm center to center is required, so we are going to provide 100 mm center to center. When you are going to see your calculation, we did the same thing, 12 mm diameter of bar at 100 mm center to center. So here also the same thing, 12 at 100 mm center to center we are going to provide, and distribution reinforcement 10 mm diameter of bar at 150 mm center to center we are going to provide. So finally this is your schedule as we did in our manual calculation, the scheduling. So this scheduling automatically sheet is going to create here. So for the stem, earth phase and other phase, on the earth phase continuous 12 mm diameter of bar at 200, and at curtail 12 at 100 mm center to center. Now distribution reinforcement 10 mm diameter of bar at 150 mm center to center. You don't need to write all these things, automatically sheet is updating everything, right? You only have to choose the values in your yellow cells, right? Now other phase of the vertical stem, so main reinforcement and distribution reinforcement is going to be provided as same, 10 at 150 mm center to center. So this is what done here, both we have provided. Now second, the base, here it is the stem, now here is the base top reinforcement, bottom reinforcement. Top reinforcement is 12 at 200 mm center to center, distribution is 10 at 150 mm center to center, and for the bottom bars 12 mm diameter of bar at 200 mm center to center, and distribution again 10 at 150 mm center to center. Now this sheet is not only giving the schedule, but also this sheet is updating the complete detail in respect of your design results. So whatever the design schedule is actually present here, in respect of this design schedule, the detailing is actually available here. So first of all we are going to read the detailing for the cantilever portion. So whatever the schedule, so as you can see, continuous reinforcement as of 12 mm diameter of bar at 200 mm center to center from base to up to top. So it is 12 mm dia at 200 mm center to center, as you can see in this sectional elevation and in this elevation, side elevation. So one bar is continuous from base to top and one bar is going to curtail. So curtailment is there 12 at 100 mm center to center. So spacing between the two curtailment bars is 100 mm center to center, and the spacing between the two continuous bar is 200 mm center to center. So this is the case for your earth phase, and for the same the distribution reinforcement is provided as 10 mm diameter of bar at 150 mm center to center. Here it is available, and here also you can see in the side elevation as 10 mm diameter of bar at 150 mm center to center. Got it? Now thereafter on the other face we have provided the minimum reinforcement as 10 mm diameter of bar at 150 mm center to center as vertical bars as well as distribution bars. So this is actually present here, 10 at 150 for the main vertical bar and 10 at 150 mm center to center for the distribution, both are same. So this is for the cantilever portion. When you are looking for the base, so for the bottom face 12 at 200. So as you can see, for the bottom face main reinforcement as 12 at 200 mm center to center and distribution bar as 10 at 150 mm center to center. So as you can find from here, it is distribution bar as 10 at 150 mm center to center, main bar as 12 at 200 mm center to center, and total thickness of the base is 400 mm is given. The height of the cantilever portion is 4300 mm. That is what here updating. Now for the hill portion, or for the top bars 12 at 200 mm center to center, distribution as 10 at 150 mm center to center. So this is also here it is present by the circle, it is what distribution reinforcement 10 at 150 mm center to center, and this is the line is actually representing the main bars as 12 mm diameter of bar at 200 mm center to center. So this is what actually the complete detailing of your cantilever retaining wall with a flat backfill. So this sheet is capable to do your complete design in just of 3 to 5 minutes only. You don't need to follow the complete manual calculation will required 1 to 2 hours. Thanks for you all for watching this complete video. Hope that you all understood all the calculation. Thank you.